the universe whispers to us. It does so through a faint afterglow, a relic of its fiery birth. This afterglow, known as the cosmic microwave background radiation or CMB, is a faint whisper of light, a messenger from the dawn of time. It provides a glimpse into the universe as it existed a mere 380,000 years after the Big Bang. The CMB is not just some faint light in the sky, it is a treasure trove of information, a cosmic time capsule that holds the secrets of the early universe. The CMB is a faint, uniform glow of microwave radiation that permeates all of space. It's often called the afterglow of the Big Bang because it is the oldest light we can see in the universe. This light has been traveling towards us for over 13 billion years, carrying with it the imprint of the early universe. Imagine looking at a photograph of a baby. That's essentially what the CMB is to cosmologists, a baby picture of our universe. The CMB is a faint signal, but it is detectable with sensitive radio telescopes. It is about 2.7 degrees above absolute zero, or minus 455 degrees Fahrenheit. This temperature is remarkably uniform across the entire sky. This uniformity tells us that the early universe was incredibly homogeneous, meaning it was very smooth and the same everywhere. The discovery of the CMB was a watershed moment in cosmology. It provided the first direct evidence for the Big Bang theory. Today, the CMB is one of the most important tools we have for studying the early universe. It is helping us to unlock the secrets of the universe's origin, evolution, and composition. In the blink of an eye after the Big Bang, the universe was a seething cauldron of energy and particles. Temperatures were unimaginably high, and matter existed in a state of plasma, where electrons and protons zipped around freely. Light couldn't travel freely in this chaotic soup. It was constantly being scattered by the free electrons, much like light scattering through fog. As the universe expanded, it cooled. Around 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, marked a pivotal moment in cosmic history. With the formation of neutral atoms, the fog lifted, and the universe became transparent. The light that had been trapped in the plasma was finally free to travel through the universe. This light, stretched over billions of years by the universe's expansion, is what we see today as the cosmic microwave background radiation. It's a snapshot of the universe when it was just a baby, a tiny fraction of its current age. Imagine a flashbulb going off in a smoke-filled room. Initially, the light is trapped by the smoke, but as the smoke clears, the light from the flash is free to travel. In a similar way, the CMB is the light from the Big Bang that was finally able to travel freely after the universe became transparent. The CMB is a testament to the incredible journey our universe has undertaken. From a scorching, opaque fireball to the vast, transparent cosmos we see today, the CMB serves as a constant reminder of our universe's dramatic evolution. The year was 1965. Arno Penzias and Robert Wilson, two radio astronomers at Bell Telephone Laboratories, were working on a new, highly sensitive antenna. They were trying to eliminate a persistent hiss in their data, a background noise that was interfering with their observations. They pointed their antenna to different parts of the sky, expecting the noise to disappear. But the hiss remained, a constant faint hum, regardless of where they looked. Little did they know, they had stumbled upon one of the most significant discoveries in the history of astronomy. Initially, Penzias and Wilson were puzzled by the persistent noise. They meticulously checked their equipment, even going so far as to clean pigeon droppings from the antenna. But the hiss persisted. They had unwittingly discovered the faint afterglow of the Big Bang, the cosmic microwave background radiation. At the same time, a team of physicists at Princeton University, led by Robert Dicke, was building a radiometer specifically to search for the CMB. Dicke's team had predicted the existence of this faint afterglow based on the Big Bang theory, and they were actively searching for it. When Penzias and Wilson heard about Dicke's work, they realized the significance of their accidental discovery. The persistent hiss they had been trying to eliminate was not noise at all, but the echo of creation itself. The CMB is remarkably uniform. However, it's not perfectly uniform. Hidden within this faint afterglow are tiny temperature variations, fluctuations on the order of a few millionths of a degree. These minuscule variations are of immense significance. They hold the key to understanding how galaxies, stars and planets formed from the smooth primordial soup. These temperature fluctuations represent regions of slightly different densities in the early universe. These density variations, though incredibly small, were enough to act as seeds for gravitational collapse. Over billions of years, gravity pulled matter together around these denser regions, forming the large-scale structures we see in the universe today. Imagine a perfectly smooth surface of water. Now, imagine tiny ripples disturbing this smooth surface. Over time, these ripples might grow, leading to the formation of waves and eventually larger structures. Similarly, the tiny temperature fluctuations in the CMB acted as ripples in the early universe, eventually leading to the formation of galaxies and galaxy clusters. These temperature fluctuations are a window into the processes that governed the early universe. They provide strong evidence for the theory of inflation, which posits that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. The study of these fluctuations is crucial for understanding the evolution of structure in the universe and testing cosmological models.